So hello everyone, this is lecture 66 for the mathematical physics. In the last lecture we were discussing about the Hermite function, and we already discussed the legendary function. We were discussing some recurrence relations for the Hermite functions, and we did up to here. So today we will see about the Bessel's function and the Laguerre function. Before that we will see the Hermite function's Rodrigues formula, that is to generate any polynomial for the Hermite. So it is h n x equal to minus 1 to the power n exponential x square, differentiation with the order of n exponential minus x square. So you just put the value of n and you can find the polynomial accordingly. So it also satisfies the orthogonality condition, but here this factor is validated, means this exponential minus x square should be there. Then hm and hn will give you always 0 when m is not equal to n, and when they are equal they will give you 2 to the power n under root pi n factorial when m equal to n. So you must remember this formula. This is a very important formula. Let's see some examples based on them. So if integration is 4x square minus 2 exponential minus x square dx, so you can see here you can assume 1 here, and this is nothing but our second Hermite polynomial. So it is h naught x h2x exponential minus x square. So hm and hn are not equal, m and n are not equal, so it will give you 0. So that's how you can solve the sum integrals of this kind. Now you have here 4x square minus 2 to the power square. You can write it as h2x 2 times h2x. So here m and n are same. So it will be 2 to the power 2 under root pi 2 factorial. So it will give you 2 to the power 2 will give you 4 to the 8 under root pi. So that's how you can use this. Now let's see today the Laguerre function. There is no much question asked from the Laguerre function, but I will tell you everything you need from here. So Laguerre function is the solutions, means these are also the polynomials which are solution of this differential equation, that is x d square y by dx square plus 1 minus x dy by dx plus ny equal to 0. When you solve this differential equation, it will give you different polynomials for different value of n, and n is greater than or equal to 0, and that is called the Laguerre functions. So let's see the generating function for the Laguerre. So this is the generating function gxt, and it is equal to exponential minus xt divided by 1 minus t, and this should be equal to ln x tn, means when you solve this and compare the coefficients of tn, then you will get your all the polynomials of ln x. Okay, and I will write directly the results, which you should remember. We don't need the proof here. So when you expand this, you will get for l0 x, l0x will be 1, l1x will be 1 minus x, l2x will be 1 upon 2 factorial x square minus 4x plus 2. So that's all you need to remember, the three starting polynomials up to l2. Now we can see some recurrence relation based on them. So you must remember this. So this is what you get when you differentiate g with respect to x or t. So these are the two relations you can use. In place of gxt, you can directly substitute this thing, and when you differentiate, it will give you ln dash x and t n minus 1. That's how you can find all the recurrence relations. So I'm not going into detail to prove them, because we did the same thing in the Hermite and the Legendary. So you can get the same results, and there is not much question asked from here, so I'm just leaving that for you. So just remember these two relations, they are important. Means that's how you get from here. Means you can directly differentiate with respect to x, you will get this relation, and with respect to t, it will give you this relation. So let's see what is important here. So question may be asked from here, that is some special values that we need to find ln at 0, ln dash at 0, and ln double dash at 0. So you can find this directly from this generating function. Put x equal to 0 here, it will give you 1 here, because x is 0 here, so this complete term will be 1. So 1 upon 1 minus t will be equal to ln 0 tn, and see if you get here, this will be 1 upon 1 minus t, and this is a geometric series, you know this. This is nothing but 0 1 plus t plus t square plus t cube plus t4. We already discussed it many times. So this will be tn. Now when you compare this with this, so ln x should be 1, because here the coefficient is 1. That's how you get ln 0 equal to 1. Now if you know ln 0, then you can find the ln dash and ln double dash. How? You know the differential equation already, so you will just substitute here ln x, ln dash x, ln double dash x, and we will substitute x equal to 0, then this will cancel out, and this will give you ln dash. So we'll get this equation after substituting the value. Now for x equal to 0, we need to find the value. So x equal to 0 will give you this term as 0. It will be ln dash 0, and n ln, and ln 0 we know that is 1. So ln dash 0 will be minus 1. So remember this result, very important. Similarly, you can differentiate this equation again. It will give you ln dash, ln double dash, ln triple dash, and substitute x equal to 0. You will get for ln double dash 0, because ln dash 0 will be minus n, and this will be 0. So ln double dash 0 will be ln plus 1 divided by 2. So that's how you can solve this also. And there is also the orthogonality in the Laguerre also. So this is means if it is exponential minus x, lmx, ln x, dx, these are some polynomials for the Laguerre, then this result will be equal to Kronecker delta. Means if m and n are not equal, then this will be 0, and if m and n are same, then this whole term, this whole integration will resolve to 1, and limit, or remember the limit, this is 0 to infinity. So remember this result, only the question can be asked from here if they will be asked. So let's see the Bessel function. So this is a very big means according to the exam point of view, from where question can be asked. So Bessel function is, again, you will get these functions at the solution of this differential equation for different n, and see what is difference here. Here n will go from minus infinity to infinity, where n is integer, so n can be negative also, n can be positive also, and for n greater than or equal to 0, you will get this is your solution. And this is again a series, means this time you will not get a single polynomial, you will get a series every time. Okay, so where j is going from 0 to infinity, and this will be your series. For n equal to 0, put 0 here, then j will be first 0, then 1, then 2, then 3, and that will be your polynomial. So this is, remember this formula to get the solutions for any particular n. So jnx is even function if n is even. So n is even, we call that jnx as even, and odd a function if n is odd. If n is non-integer, then jnx has no such simple symmetry, means then this solution will not be valid when n is not integer. This is for n greater than 0 and integer. So first we will discuss this case when n is not n is the integer. Then we will discuss the case also where n is not integer. So first let's see for the n equal to 0 what will be our polynomial. So n equal to 0, substitute 0 here. It will be minus 1j, j factorial, x by 2, 0 plus 2j. Now put j equal to 0 first, it will give you 1 here, and 1 here, so it will be 1. Then put j equal to 1, it will give you minus, and minus, it will be minus here, so x by 2 square. So j is 1, so it will be x by 2 square. This will be your second term. Now put j equal to 2, it will give you plus 1 here, and 2 to 4 here, so it will be x by 2 4, and 2 to your 4 here. So that's how you get your series. Means this will be your the first polynomial, that is j naught x, and this will be a series. Now for n equal to 1, it will be 1 here, and again put the value for j equal to 0, then 1, then 2, and 3, then you will get your series. Now see, if you take this will be your series definitely, and if you take x by 2 common from it, this will again give you means this result. Okay, forget about it, just listen here. Means you have j1x, this will be this, and you have j0 x, this will be this. You know how to find this, I already told you. Now let's take this j0 and differentiate this. So j0 x, what we will get? This will give you 0 here, then it will be minus 2x by 2, and 1 by 2 will be outside. You know how to differentiate. Then differentiate this and this. So you will get a series again for the j0 dash x. This will be this. Now take the x by 2 common out of here. So what you will get? Let's take the minus x by 2 outside. It will be 1 then, and it will be 1 upon 2 x by 2 square. So after taking the minus x by 2 common, you will get this series, and whatever this series is, just see here, this is nothing but j1x. This complete series with the x by 2, this is nothing but j1x. So after taking minus outside, this is, we will get the j1 again. So we can write j0 dash x is nothing but minus j1x, and j1x will be equal to minus j0 dash x. So this is a very important result, you must remember this. Okay, j1x is nothing but minus j0 dash x. So we'll use this thing. So you must remember this, and how we will get this. Now let's see the generating function for the Bessel's function, and it is only for the integer. Means integer can be of any sign, it can be negative also, positive also, but not the non-integer. For integer n of either sign, this will be your generating function. Gxt equal to exponential x by 2 t minus 1 upon t, and this must be equal to gnx dn, so that we can find the gnx. So, and you must remember this result. Means we are not going into the proof. This is the result, that j minus nx equal to minus 1 and jnx. So we already find it that how to find gnx. So this was the result, how to find gnx. And if you need to find the j minus nx, then you can just use this formula. Means for the j minus 1, put 1 here, then it will be minus j1x, and for the minus 2, it will be 2 here, it will give you j2x simply. So that's how you can find all the negative terms, and the positive you already know. So this is a relation, very important. Now let's see some recurrence relations. So find the del g by del t again. It will give you x by 2 1 plus 1 upon t square exponential x by 2 t minus 1 upon t. So this is the differentiation with respect to t, partial differentiation, and this must be equal to this. Now see, this is nothing but, this is again the same thing, equal to j n x t n. So we'll substitute in place of this. This must be equal to this, and we need now we need to compare the coefficients of t n minus 1, because this time we are having t n minus 1 here. So let's compare. For that, what you need to do is, first it will be x by 2 j n t n. So put in place of n minus 1. So it will be j n minus 1 x by 2 j n minus 1 x for the first term, plus second will be t2 will give you t n minus 2 here, and that should be equal to n minus 1. So in place of n minus 2 we will substitute n equal to n plus 1. So that's why you will get j n plus 1 x by 2, and that will be equal to n j n. I hope you got this point, how we write it this equation. We need to compare of n minus 1, so we'll multiply tn in both the terms. So here you will get n minus 2, here you will get tn. So you will substitute n minus 1 here and n plus 1 here to get the n minus 1. So this is your first recurrence relation, remember this. Now let's find the second one. So differentiate this generating function again with respect to x partially. So this will give you 1 upon t minus 1 upon t exponential x by 2 t minus 1 upon t. So this is again j n x t n, and this should be equal to j n dash x plus t n, because you will differentiate with respect to x, it will give j n dash x, so t n. Now this is equal to this, because this is your generating function. Now we need to compare the coefficients of tn. So let's compare. First it will be tn plus 1 here. So tn plus 1 in place of, we need to write n equal to n minus 1. So first term will be j n minus 1, and second will be 1 upon t tn. It will give you t n minus 1. So how you get tn? So put in place of n plus 1. So it will be j n plus 1. So we'll get 1 upon 2 j n minus 1 minus 1 upon 2 j n plus 1 x equal to j n dash x, after comparing the tn coefficients. Now just to take the 2 LCM, it will give you j n minus 1 x minus j n plus 1 x equal to 2 j n dash x. This is your second recurrence relation. So remember these two relations for the Bessel's function. This is your first, this is your second, and you can verify these equations very easily. Just to place n equal to 0 here first. So it will give you j minus 1 j1 equal to n is 0 here, so it must be 0. So from here you can see j minus x equal to minus j1x. So you can see this result, we already proved this, means given you the expression. So it will be j minus 1 n equal to 1 will give you minus j1x. So means this recurrence relation is true, because it is giving us the same result. Now let's see for the second one. Put n equal to 0, it will give us j minus j1 equal to 2 j1 dash x. So n equal to 0, it will give us 2 j naught x. Now see, we already proved this result. So j minus 1 will be minus j1. So it will be minus 2 j1 and equal to this, 2 will cancel out. j1x will be minus j naught x. So we already proved this result here. So this relation, this recurrence relation second is also valid. Now let's see some important results. dy dx of x and jnx, if it is there, then you will write it directly x and jn minus 1 x. And if dy dx x minus n jnx should be equal to minus x minus n jn plus 1 x. And third is jnx equal to plus minus j dash n plus 1 n plus minus 1 x plus n plus minus 1 divided by x jn n plus minus 1 x. So I'm not going to prove them, because you don't need the proof in exam. You just need these relations to solve the questions directly, and you can try to see that if they are true or not. Just put n equal to 0 in the first equation. What you will get? You will get j naught x, means j naught dash x, and here it will be 1 and j minus x. So again you will get the same relation which we proved. So means this relation is true. Similarly you can prove all these relations, they will be true. But the main point is you must remember these results, okay, because they are very important. Now let's end today's lecture here. In the next lecture we will see some non-integers for the n value of non-integer Bessel's function, and we will see the different functions we have discussed already and the singular points about for them. So then this swell function will be ended. Okay, we'll meet you in the next lecture. Thank you everyone.